Okay, so now let me summarize. It's like what we've done so far in terms of numerical methods for solving algebraic equations. Okay. Okay, so first we looked at nonlinear scalar equations. Right? So I was looking for the roots of f of x is equal to 0, where f is a scalar value function. And we looked at a bunch of methods, such as bisection, which has a linear rate of convergence. And is robust in the sense that if you have an initial interval where the function changes sign, then the bisection method is guaranteed to give you a solution with a very sort of well-defined rate of convergence. You get one binary digit of accuracy for every step. The second method is the method of false position. And in general, you have superlinear convergence. To that. Then the third method we saw was Newton's method, which has a quadratic rate of convergence. But you need a good guess. Okay, and then the fourth method is the secant method, which is slightly slower than Newton, with the advantage that you don't need the derivative. Okay. All right, so that's some of the methods which we looked at. It's like for nonlinear scalar equations. The second set are for linear systems. Ax is equal to b. And so the first thing we looked at was just forward and backward substitution. And of course, that only works if you have lower or upper triangular matrices. Okay. Then the next thing we looked at was Gaussian elimination. Where we use elementary row operations to reduce the matrix A into an upper triangular matrix. All right. And then once you've done that, then obviously you can apply sort of backward substitution, for example, right? The third thing we looked at was LU decomposition, where you end up with a factorization of the matrix, A equals to LU, right? And what happens then if you have a linear system which involves a matrix A, it's like which has this LU factorization, then you can apply forward and backward substitution to solve the system. And then the last thing we did was to do partial pivoting for LU. Right, and that gives you a factorization which says that P times A is equal to LU, and this is a stable version of LU, right? So the problem is that LU can suffer from small pivots, it's like which destabilizes the solution, and partial pivoting, it's like addresses that issue. Okay, and then the third thing which we just sort of looked at was nonlinear systems. So some vector valued f, which applies to a vector x, right? So looking for the sort of the zeros, it's like of a system of nonlinear equations, and what we did here was Newton's method for systems. Okay. So that pretty much wraps up. It's like our discussion of, it's like how one goes about solving sort of systems of equations or equations, linear, both linear and nonlinear. You can go much deeper into this. This is really just scratching the surface in terms of some numerical methods. In particular, there are a whole bunch of different types of methods based on different forms of matrix factorizations, which I won't go into. It's like in this class. But if you were to take sort of a more advanced numerical analysis class, which focuses on numerical linear algebra, for example, it's like then they will go into much greater detail. It's like about the types of matrix factorizations and other types of iterative methods as well. Okay, I guess I should have said that in addition to that, we also talked about iterative methods here, right? So there's also part E, which is sort of iterative methods. So for example, Jacobi and Gauss-Seidel. Okay, all right. So, and I should just sort of remark that where it becomes challenging is how to do these kind of things stably, and how to speed up the computation. It's like for iterative methods. So there's an issue of conditioning. It's like of the linear system. It's like which becomes important. As you go deeper into the subject, there's the subject of what's called preconditioning, which more or less allows you to, it's like massage the system of equations in such a way that they converge much more sort of quickly. It's like using various types of iterative methods. Okay, so again, it's like we've barely scratched the surface. It's like of the kind of methods one would sort of bring to bear. It's like for these problems, and again, it's like the challenge is particularly sort of focused on large-scale systems of equations, perhaps with some sort of sparsity, or perhaps with some sort of conditioning issues, right? So those are the type of things. It's like which, if you were to take again a more advanced class in numerical linear algebra, you'll spend a lot more time doing. Okay, so anyway, so that's what we're going to cover. It's like in terms of solutions of algebraic equations for the purposes of this class, and then we're going to switch to a different subject right now. All right, so I'll stop here.